Hello, everybody, and welcome to the 44th episode of the Hyperthesis podcast. Today, we're joined by our special guest, Andrew Kovachik. We'll introduce him in a moment and come to his research. But for now, I'm Liam.
My name is Svili.
I'm Patrick.
And I'm Andrew.
So welcome, Andrew. Andrew is a master's student at McMaster University, so he's one of my friends. We've taken some classes together. You did your Bachelor of Science at Waterloo in physics, and now you're working for Sergey. Sergey, I forget how to say his last name.
Yeah, I've gotten a lot of practice now. I say Sergey Sibiryakov.
Okay, so Sergey Sibiryakov at McMaster University. So we'll come to what you study later. It involves quantum gravity. But first, we'll get into some potential intro topic. So does anyone have anything prepared for that?
Yes. So, last night I saw Interstellar for the first time in IMAX. I've seen it before in regular format, but they had it hosted at a local IMAX theater. And during one of the scenes, spoiler alert, the main character is falling through a black hole and into a black hole. And ends up the black hole is actually a tesseract thing, and that's a whole other story. But it got me thinking about what's inside a black hole. And we know that black holes are kind of the heart of darkness. They are these infinite voids of matter that even light can't escape. But I was thinking, inside a black hole, is it bright? Because if you think all the light that's coming into it is moving towards the center, and if you're falling into it, you're also moving towards the center. So if you were to look behind, would it be very bright? Or if you were to maybe not so much look ahead because the light wouldn't be reaching you, but if you were to look behind, would it be bright inside?
I think so. There are these simulations people have made of like what it looks like to fall inside of a black hole, and they've put them on the internet somewhere, and it's been a long time since I looked at one of them, but I think when you fall through a black hole, you don't actually see the horizon. It's not, maybe Andrew knows more about this because he studies black holes. I study black holes a little bit, but not quite as much. So when you fall through a black hole, from your point of view, you don't really see the horizon because as you fall past it, I guess it gets complicated, but all the light that's when you're in the black hole, yeah, you can't see anything ahead of you, I think, because the space-time there is curved more than where you're at. And I mean, this is all assuming you are not affected by the black hole, because I think in reality you get stretched out a bunch. If it's a small enough black hole, you do. If it's a really big black hole, maybe you don't, because the tidal forces are a bit more gentle. But yeah, I think you see everything falling in behind you, but maybe there's some like red shifting or blue shifting stuff that happens, so eventually the visible light would change and you wouldn't see it. But maybe if you could see every spectrum, maybe if you were a mantis shrimp falling through a black hole, you could see more.
Yeah, I think the point I like to make is also like, well, in past the event horizon, would it remain like the typical photons that we can observe at all? Or just like, well, if you're inside the black hole, it's just another state of matter that just, it's not observable in a way to say bright or dark.
I guess also with that, I imagine the photons might be blue shifted, like to X-rays, gamma rays, or even higher energy, just as they move towards the center and gain a whole bunch of energy. And so, I mean, would you just be completely irradiated with very, like, I don't know, high power cosmic rays kind of thing?
Yeah, I love this question. I always have this image of these Penrose diagrams in my head, which Liam's probably a little familiar with. And they show you the regions of space that are kind of causally connected. And when you cross over the horizon, you're going over like this 45-degree angle line, and that's the fastest you can go in these spacetimes. And any path you take over this 45-degree line, you can move over it totally fine. And it's like walking through any other space and time. It's like walking through a doorway. It's just then, if you ever try to go back to that door, it's like it kind of keeps racing away from you. But you keep seeing people walk out of that doorway and they can come to you all the same. So you can keep seeing like these rays of light coming in through this horizon. And so, yeah, I think everything feels very normal, I believe, when you go through the event horizon, unless you try and leave.
Yeah, and that's something that I always thought was interesting. Like, that's relativity, right? Everything is different depending where you are, like, outside of a black hole. Even with Hawking radiation, I think, like, we always bring up black holes and Hawking radiation. I'm sure I've said this before at some point, but yeah, Hawking radiation is something that like a faraway observer, at least according to our current theory, would see. But if you're falling into a black hole, you won't see Hawking radiation. It's all kind of observer dependent.
Yeah, that is very interesting. And one thing that Andrew mentioned was the Penrose diagram. And to me that has two meanings because I used to study tensor network and stuff. And Penrose diagram is the connectivity of tensors. But I don't think that's what you're talking about here, right?
Yeah, I haven't heard about them in this context. I'll have to look them up after. So, yeah, Penrose diagrams, it's this really cool way you take the entirety of space and time. So you have something that goes to infinity, and it's a way of compressing those infinities down to kind of things you can see, right? So I might be getting my trig function wrong. I think it's arctan, right? If you take, for the inverse arctan, or
yeah,
I'm saying the wrong trig function.
It's a tan or an arctan, depending on how you look at it. It's one of them.
Because the inverse of the tan function, if you take something from infinity, it maps to 1. And if you take something from negative infinity, it maps to -1. So
that's arctan, yeah.
Yeah, so you can take your whole space and time and you can compress it down to this thing that you can physically see.
Yeah, it's actually, Penrose did some really nice things. That's but yeah, so there's these things called Penrose tiles, I think, and that's what sometimes they're called Penrose diagrams, maybe, and that's what Feely's talking about. So there's actually, it's just one of those like bad terminology things where there's two different types of Penrose diagrams. It's like a Euler equation. Like Euler is this mathematician who has about 12,000 equations named after him. It's like, which one do you mean? Right? Like, so yeah, Penrose diagrams are really, that's what you do in gravity a lot, is you take your infinite space-time, you kind of say, that's really hard to look at, let's transform it and compress it into some finite region that's easier to visualize. But you have to do it so that you do it conformally is what it's called, I think. They're called conformal diagrams because you have to use a transformation that preserves the fact that the speed of light is the speed of light. So you can't do it so that things like that change.
What's we did similar thing in GR, right, where what's that light cone or like what's it called, space-time axis thing that we use to map what's called constant acceleration? Remember, Liam?
Do you mean Rindler coordinates?
Yeah, like Rindler. Yes, Rindler coordinates.
I think that's something different.
It's a similar idea because Rindler coordinates basically like remapping your 0 to infinity or minus infinity to infinity in a specific way that fits. Well, just coordinate transformation.
Yeah.
Our Penrose diagram just coordinates transformation.
Yeah, well, Rindler coordinates, it's like in special relativity, you can always move to the frame. It's all about frames of reference, right? Like if I'm on the Earth watching a rocket ship go by, I see something. And if you're on that rocket ship going by, you see something maybe slightly different from your point of view. And I think Rindler coordinates are just, if you're accelerating, what does the person who's accelerating see opposed to someone who's watching them accelerate? Whereas these conformal Penrose diagrams, they're not so much about what reference frame you're in, I think. It's more so like you're just mapping space-time to a specific region, and then you can start dealing with what frame you're in then. So it's a little different, I think. Maybe Andrew or Patrick knows.
I do just want to comment that we went more in depth with relativity in our special relativity and our not so special relativity, our general relativity episodes. So go give those a listen if you need to catch up, and then come back to this point.
Yeah, I think on the Rindler coordinates, that's kind of the exact mentality you want to have in mind. with a Penrose diagram, you would just take that a step further. So yeah, to get Rindler coordinates, you're doing this transformation of coordinates. But if you draw out diagrams of, say, equal time or equal distance in Rindler coordinates, you still have these lines going off to infinity. And so then there's some... It's hard to interpret those things, right? Because you want to see how it looks at infinity, but you can't. So then you would take those coordinates, your Rindler coordinates, and you would make a Penrose diagram out of that. And I think what you would see is this thing that accelerates off to infinity, that thing is going to be causally connected with the 45-degree line from that stationary observer. So the Penrose diagrams give you this cool way of seeing, hey, is that thing at infinity actually causally connected with my light cone for the stationary observer?
Yeah, for those who might not have heard of a light cone before, I'm trying to think of a good way to describe one, but basically in space-time, if you do something, if you send out a photon, or I'm trying to think of a good analogy, but basically because things can't move faster than the speed of light, there's only so many regions in space-time that you can interact with. It's like you can't go back in time, or you can't move faster than light. So because of that, in space-time, there's only specific area or specific points in it that you can interact with, and a light cone describes all of those ones that you can interact with.
Yeah, it's basically causality, right? So
Yeah.
so if there's a region where it's let's say there's like 1 second limit, right? So you can access all these space that within speed of light times 1 second in distance. So anything outside like that, let's say let's go 1c. If you have space that's 2ct away, right, then it's not accessible, so it's not causally connected. So in a way, the light cone is a way that we can visualize that and make sure when we draw stuff when we do research or we take care of causality, that make sure that all events are causally related.
Yeah, I guess like if I wanted to send a light wave to Pluto right now, 1 second from now, that's outside of my light cone because it takes light longer than 1 second to reach Pluto because Pluto's so far away. So Pluto is outside of my light cone 1 second from now. But yeah, so to wrap it up, I think if you're falling into a black hole, you'll see everything coming in behind you. But maybe they won't see you. I'm not sure about that.
Yeah, I guess you would see things behind you, but not ahead of you. And chances are, if it's a small enough black hole, you'll get spaghettified pretty soon anyway.
Yes. Make sure if you're going to fall into a black hole that it's a really, really big one so that you don't get your legs stretched out very far away from your head.
And
Yeah.
also take notes.
Maybe if we have infinite time, right? Like, the thing is, maybe you will see something in the black hole, like when you're inside eventually, because the time is so stretched, but might take like forever to you start seeing anything.
Just a tangent on the fact that this was coming from Interstellar. One of my first dates with my girlfriend, I told her, hey, we should go to this movie. It's about space exploration. And I thought it was just going to be this light, kind of fun movie. And we go, she had no idea about the movie. She didn't tell me for 2 years later. She had no idea at all what was going on in the second half. It's just a wonderful movie, eh?
Even when I saw it, I remember, like when I don't want to spoil it. I mean, it's been out for a while, so even when they go to that water planet and they're like, "Whoa, the beacon's been on. Like, why are they not here?" It's like, well, from their point of view, they only landed like pretty recently, right? And from us on Earth, it's been like many, many years. And I remember being like, "Wow!" Like, even though I know how relativity works, that still like surprised me for some reason. Also funny. I was at IMAX last night too, Patrick. I saw the new Spider-Man movie, which was incredible. I was a big fan.
What?
Like the animated one, like the Miles Morales one.
Okay.
Oh, there's a new one?
It was really good. It was really good. I was a big fan. The animation style is so good. It reminds me of like anime, and I love anime animation so much. It's just, it's incredible. But anyway, for the sake of time, we should move on to talk to our guest about what he does. So yeah, Andrew studies correct me, is it Hořava or Hořava? I've heard both.
I say Hořava gravity.
Okay, because it's spelled Hořava, but Sergey calls it Hořava, and he's like probably one of the world's top few people on it. So you study quantum gravity, so we've mentioned it before, but quantum mechanics and gravity are these two separate theories, and we're trying to unite them. And it turns out that's really hard because we haven't been able to do it yet. So there's a lot of people working on it in different ways. There's different theories. And the one you work on is called Hořava Lifshitz gravity, which you study with Sergey.
Correct, yeah.
So can you tell us about that a little bit?
Sure. So yeah, I'll try and motivate, I guess, what Hořava did. So one of the issues, if you try and quantize gravity, and I'll just say a word, but I don't think you need to know it, is you'll get these integrals when you try and do a quantum field of this thing. And those integrals have something that looks like 1 over momentum to the 4. And so if you expand this it's a 4 momentum. So if you expand the 4 momentum, you'll have terms that are like 1 over the frequency to the 4th. What frequency to the 4th basically means is you have a 4th order derivative in time. And if you solve this is just kind of a classical issue. Your solutions become super unstable. So if you think about quantum fields, which have all these fluctuations, having something which, is unstable to fluctuations is really bad. You don't want this. So what Hořava did in this very, very wonderful paper is he said, okay, well, maybe we're just wrong about what the 4 momentum looks like if it's to the 4th. Maybe there's this anisotropic scaling. So, your space, maybe that's something like to the 4th, and your time, that's something like to the power of 2 or something. And this makes quantum just completely renormalizable. You still have to do all the work to figure out how this looks, but, this solves that issue. But what people are concerned by is on the large scale, well, suddenly you're not treating space and time equal, right? So you completely lose Lorentz invariance. You lose the speed of light being constant. The good side is that this should only appear at really high energies. And so that's kind of where my field of research is. So we're saying, okay, let's take this thing that should work on the quantum level and let's see how it looks on the large scale levels where there's really high energies and where there's not like Lorentz invariance and there's not constant speed of light.
Yeah, so it basically, it looks like regular, I mean, it has to, right? So it looks like regular general relativity on typical scales. So like, you look at a planet, you're not going to see things moving faster than the speed of light. But if you zoom in really close to a black hole on the Planck scale and you get these really high energies or something, you might see something different. So I really like your theory because it relates to my work a lot.
Yeah.
These Lorentz violating things, even though they cause problems, they solve some other problems.
Yeah, I think the thing about quantum gravity is that it's so out there for most people, including me, because when you have normal physics education, quantum and relativity, or even quantum and gravity are studied they're almost mutually exclusive, right? Like we kind of aware that they don't mix, but we never really was explained why mathematically, because there's no course called quantum gravity. I mean, in undergraduate level at least, and it's always a great source of confusion to me. And it's kind of pretty obvious in a way when you study them separately that why the mathematical formulation don't really work together. But it was like, could you imagine, right? Like, well, why not? Well, why can't just have quantum thing in curved space time? And sounds easy, right? Instead of all these space, just curve it, man. But I think it's more complicated.
Even at like an undergraduate level, which is where most physicists, most of your education, like most of your general knowledge comes from your undergraduate, and then you get really, really honed in on one topic during your master's and PhD typically. But even during your undergraduate, most people don't even learn quantum field theory, right? which connects quantum mechanics with, well, it's like it takes into account, it's quantum mechanics, but you can now have a changing number of particles, and you have this vacuum thing, which we've talked about a bunch before. But you need quantum field theory. If you want to connect quantum mechanics with special relativity, you need quantum field theory. And that's like, if you want to do quantum mechanics and general relativity, you should probably understand quantum mechanics and special relativity first. So again, that doesn't really get taught to a lot of people typically. So how are you ever going to understand quantum gravity? So it's very much like one of these topics that you hear talked about all the time, but a lot of people just don't have any experience with. And even like me, right? Like I've had a little bit of experience with it, but not really. Like I've never we took that quantum field theory and curved space-time class, but like I wouldn't call that quantum gravity, right? We were still using classical general relativity. We weren't taking the metric from general relativity and quantizing it or anything, right? Like
this is a little tangential. Someone you might like to have on is Yuri, because he also works in Hořava gravity, but he's kind of working at the other extreme. So his work is saying, okay, we have this theory which we can quantize now, and we can do scattering amplitudes. We can find how these gravitons should interact. And so he's looking at these amplitudes, and spoiler, there's a lot of calculations. Yuri is a very, very smart man, and his work bewilders me sometimes.
Yeah, I think he was like the star. I think he's Sergey's like star pupil.
Yeah, 100.
We wrote this. I don't know if you got that question right with the we wrote our QFT and curved space-time exam, and there was the first question was, if you have a mirror that oscillates back and forth, it will emit particles like a black hole or whatever, right? And it was basically like calculate that. And I mean, I don't know about you, but I got it wrong. And I think some of the people I talked to got it wrong, but I think Yuri was like one of the only few people to get it right.
Yeah, that was a very tough exam. Learned a lot, but yeah, there were some tough questions, and I didn't ask Yuri how he did, but there was definitely a certain level of confidence that he had that was not there.
I remember I talked to him about it at one point, and I was like, how'd you even do that? He's like, oh, it's easy, you just get a delta function. And I was like, I didn't get a delta function. How did you get a delta function? Anyway, back to the topic. So yes, so that's the motivation for Hořava Lifshitz gravity. I always just call it Hořava gravity. Lifshitz has enough. If it's the same Lifshitz I'm thinking it is, he's got his name in enough things. I don't need to say it too many times.
Yeah, if it's the same Lifshitz, I know. He also does StatMech stuff too. He wrote a nice textbook with Landau Lifshitz.
There's a like Landau and Lifshitz textbook on pretty much every topic.
Yeah, it's like a very, very good graduate level, like research level. It's a StatMech book for people who already know StatMech and not just work on StatMech, but work on very theoretical StatMech. It's like, you want to know normal StatMech, that book is out of reach still. It's insane.
It's exactly that Lifshitz, and it's exactly coming from the Landau Lifshitz kind of phase transition type work. So I think his paper is titled Landau Lifshitz Phase Transitions in Quantum Gravity. It's exactly what you're thinking of. Right, so with this motivation out of the way, the work I'm doing is, if we have these really high energies around black holes, that should hopefully give us some different prediction that we can go out and observe somewhere. So this, if you ever try and solve Einstein field equations or anything in GR, it's really tough, so you have to make a lot of approximations. So what we wanted to do was to find solutions for moving black holes. So previously, people have found solutions for stationary black holes and rotating black holes in this theory, and they get these sensitivity predictions. So, if it's rotating and if it's actually Hořava gravity, your gravitational waves might be tweaked by this amount in this frequency range or whatnot. So we want to get these for the moving black holes, because that's a pretty physical thing you're going to see in space, is black holes moving away from you.
Well, aren't moving black holes just a matter of a reference frame?
Yeah, this kind of gets a lot of people, including me, is it is a matter of reference frame, but these transformations are non-trivial anymore. So before, when you did have Lorentz invariance at low energies, yeah, you can just change your reference frame and you're all good. In Hořava gravity at these high energies, you can't just do these trivial transformations anymore. You could, but it's really hard. So yeah, we have to do a bit of work. So what we do is finding solutions to Einstein's equations are really not easy at all. So there's some really classical ones like Schwarzschild solutions. So what we say is we work in like a decoupling limit. So we're going to work in a region of this theory where the black hole's moving, but it's going to move slowly. So then you can take your solution to be something like Schwarzschild plus some perturbation to this. So that's a lot of work.
Yeah. Oh, now I know you really study these space-time stuff because you say Schwarzschild instead of Schwarzschild, which some people do, right? And I mean, fortunately, our undergrad professor is German, so he can like nudge us towards the proper pronunciation. But back to the topic a bit. I thought, in the grand scheme of things, the point of quantum gravity is to basically create a unifying theory of everything, basically a grand unified theory, right? Because now the four out of the four forces, the three are kind of really mixed together. So in a way, how does your work kind of help related to this kind of unified theory thing?
Right. So in terms of the maths of Hořava gravity, it kind of just works, right? It gives you a theory of quantum gravity, but a lot of people have come up with theories of quantum gravity. And so it's about trying to find these ways of making the predictions. So the idea being is it seems pretty hard to actually scatter gravitons. We haven't seen them yet. So that might not be a feasible prediction. But something we actually have really good measurements of now from LIGO, LISA, I think, what's the other one? Einstein detectors coming soon. These things make really good measurements. So the hope is you find where this deviation should lie if you actually are working in Hořava gravity. And this is just one of those regimes where we can make useful predictions.
Yeah, so I'll come to this a bit later but like you say, there's all these different theories of quantum gravity, and like string theory and loop quantum gravity are ones I'm going to talk about later. They're two big ones, but I mean, again, your theory isn't really that useful if you can't experimentally prove it or use it to tell you something, right? So I think that's the huge problem. Well, I don't want to say it is a problem, but it's the huge like topic of research in quantum gravity, is like trying to come up with something you can measure to like say, okay, this theory is wrong or it's right, or just anything, because quantum gravitational effects are very, very, very tiny. And even at the most extreme places like black holes, they're still pretty small. So they're hard to measure.
Yeah, and I've talked about this with Sergey before because, there's this kind of pessimist in me, which is, okay, there's a lot of theories of quantum gravity. Why are we thinking ours is going to be right, And I think the resolution I've come to this is right now we just have no observation to lead the way, right? At least kind of in the 90s when you had quantum evolving and particle physics evolving, they had a lot of hints and observations to kind of guide them, and we don't have those right now. So I think the best approach you can do is try and take just a very reasonable idea, which I think Hořava gravity is, and maybe it's not the right thing, but hopefully if it's reasonable enough, you might be able to find an observation that will eventually lead you to a better theory.
So I'm curious, what would these observations look like? I have an experimental background, so I'm always interested in how we can actually prove these things. So what would these observations look like? And do we have the technology now to actually make these observations? Like if you had the exact right conditions and knew what you were looking for with LIGO, could you actually confirm these theories?
Right. So I need to find this out by the end of the month, unfortunately. So right now I have the solutions to the equations for these black holes moving. And what I'm trying to do now is you want to match these solutions at asymptotic infinity. And then these give you these sensitivity parameters, they're called, which say, okay, if this is the true thing, it's going to look like regular GR plus this little bit in this frequency range. So the hope is, fingers crossed, that this is going to be something substantial that is observable. And so, maybe it's like 1 in 10 to the 8th, right? That's something that the future gravitational wave detectors will be able to measure.
Still pretty small, but
yeah, it's one of these kind of give and take things where you want it to be small enough that it wouldn't have been observed by the current gravitational wave detectors, but you want it to be substantial so that in the future gravitational wave detectors you can see this deviation.
Is it some kind of like corrections to, let's say, what we expected prediction from normal GR, but you know what? We see these little peaks or little fluctuation could be explained by almost like maybe some alternative theory of gravity or this type of like quantum gravity.
It's exactly like that. The way I tend to explain it to my family is if, you're trying to do some mental math and you have some weird fraction, like say 57/70. Okay, that's hard to give you a decimal in your head, but you can kind of quickly split it into like 50/70 plus I forget what number I said, the 6/70. And so, you already know what the 50/70 is, but then you're trying to get more precise and find out what that smaller fraction is, and then the smaller fraction.
Right. And I actually want to go back on leading back on your kind of life story a bit. So I think when you move into grad school, especially in field like quantum gravity, that must be quite like a academic shock. What was it like? Because I work on StatMech. I know StatMech a bit before, but to me, I feel like the world opened up to me. Like there's so much I didn't know about statistical mechanics. I'm sure for you, because I know for sure that Liam, it opened him up to so many fields that might not be able to study it extensively and undergraduate. What was it like for you when you get into quantum gravity? Was it like such a shock, the amount of the depth that you have to go into theoretically? Like what was it like?
Yeah, it was absolutely terrifying. It was just so much more in depth in everything. It was more papers, it was more mathematics, it was more fields of knowledge you needed. There's this, I'll tell you a story here that I think was hilarious. God bless Liam. At the start of my time here, there was this pairing of senior master's students and an incoming master's student, and so I was paired with Liam. And so Liam took me out for lunch one day, and he was telling me about his research, and he was asking me, is there a connection here? And I had been doing this, 2 weeks, and I was like, Liam, I don't see it. I'm not sure. Yeah, okay. So we come back from lunch, and we meet Sergey by his office, and I introduced Sergey and Liam because I think Sergey was on your
new. Yeah, Sergey, it was like he was new, very new. I think I never met him before.
Yeah, actually. And so Liam introduces his work, and then Sergey goes, Andrew, this is very closely related to your research. And God bless Liam. Liam just goes, oh yeah, Andrew was telling me that over lunch. Thank you, Liam. Thank you.
Well, I think you didn't quite get the connection immediately because you were there for 2 weeks, right? Like you had no idea what you were even doing yet. It took me like 1.5 years working with my supervisor to understand what I was doing. Like it takes a while usually, but like I don't think you got the connection. But the things you were saying were the exact same things that like I was doing, and I'm like, oh yeah, they're related.
Yeah, so it took a while. I don't think I really quite found a groove with it all until maybe a year and a bit. to kind of even understand what I was doing. It takes a long time, especially when you're doing classes and TAing. It's really hard.
So I want to go, trace back slowly, chronologically. So what made you interested in the quantum gravity or working with Sergey? Like, what piqued your interest? Like, when you apply for grad school, like, what, I want to work on quantum gravity. That thought never came to my mind. Actually, it might came, and I just kicked it out of my head, like quickly, because like, well, testable maybe. I don't know,
Yeah, it's exactly that. I thought it was something that could be testable. Just, when you're an undergrad, you have these opinions, but maybe they're not totally sure. But I had this opinion in my head that it seemed like that the classical way of testing particle physics was maybe going to be pretty hard to do in the future. Large Hadron Collider, I think that was a great success. I think it found everything it was looking for, but we didn't really find much more than that. And these larger and larger improvements to it, I think it increases the energy levels by an amount, but for the amount you're scaling up, it didn't seem like a lot. And so I kind of had some slight doubts on how likely this field of physics was to make new predictions. Whereas I think I was starting to be under the impression that we were getting pretty good at looking out into space and finding particle research in that way, right? And I think that was probably a good guess. I think in that time, we've imaged a black hole, we've seen gravitational waves now, and these predictions are getting better. James Webb is a phenomenal telescope. It's amazing what that has done. I have a bad thinking of time. It feels like it's been just a couple months, right? So I was trying to look for kind of theoretical work that was going to lean towards that looking out into the universe way of making measurements. And so, then you just start going through every university's page of professors and trying to find someone that kind of fits that bill.
Because we know a guy who just finished his master at LSU, and I know like Louisiana State University, apparently they have a huge quantum gravity group there too.
Mm-hmm.
And yeah, I was surprised because I know people make effort to do quantum gravity stuff, but I didn't know it's like that big of a thing. I thought maybe it's like when string theory came along and it was hot for a while. That's part of me when I was finishing undergrad, where I looked at different fields. Like, well, it seems really hot now, right? But it could be hot for a long time, but it could also be like string theory.
Yeah, and I think it's kind of good to find the promising aspects of these theories. Like, string theory has kind of fallen out of fashion, but, Liam can attest, in all of these QFT courses, you're still hearing tons of references to string theory, or just because, although we haven't seen it and it maybe seems a little unlikely now, the work that was done in it, because it's pretty mathematically solid, and I think it's pretty grounded in reality, the ideas, you still get a lot of ideas that hopefully when you start to inch towards what the right idea is, you have these ideas to pull from.
Yeah, I'm a big believer that even if one theory is not particularly useful on its own directly, it's still pretty useful in a lot of ways. We had an episode recently on the one electron theory, if you've ever heard of that, Andrew. The idea that every electron in the universe is actually a manifestation of a single one that just goes backwards and forwards in space-time. Which is that comes from the analogy that like a particle moving backwards, it's like a particle moving backwards in time is an anti-particle moving forwards in time or something. So that was the actual theory that I think it was John Wheeler came up with it, and he had a phone call with Richard Feynman, and then Feynman in his Nobel Prize speech, he said, I didn't really think that idea was my favorite thing, but he used the idea that a particle moving backwards in time was an anti-particle, and that was what he used to help develop QED. So
That's
even if the one
amazing.
electron theory is kind of silly on it, every theory, if it's mathematically sound, it might sound silly, but it could be true. But even the one electron theory, it wasn't directly, I guess, useful. but it became useful because it led to the development of quantum electrodynamics, which is, like our best theory right now.
That's
well,
a great
don't take
example.
Liam too seriously. He's not a true believer in the one electron.
No, I'm not.
But I want to go back further into Andrew's life. So, what got into physics? We heard a lot from different story from our guests. Some people are late bloomers who just got into physics in undergrad. Some people, at 6-7 years old, they love science. They do stuff. So, what was your story like? Were you very young scientist at young age, or when did you start getting into mathematics and physics? What was this like for you?
Yeah, that's a that's a tough question. In terms of mathematics, I think that was even in elementary school. I just remember there was some teacher, and it was he didn't really have a scheduled mathematics program. It was like, hey, if you finish this chapter, just go to the next chapter. And I just remember I had so much fun. That was Mr. Richworth. And I think me and 2 other students, we were like 20 chapters ahead. And it's not, I think, because we were smart or anything. I think it was just we were really into it. It's like you keep learning and learning. And sometimes it gets really exciting, right? And then I don't think I had much knowledge of physics until grade 10, when I was trying to I took grade 11 physics, and my teacher there was Mr. Verzinga, and he was just pretty an eccentric guy. And yeah, he started talking about some physicists, and he mentioned Feynman at some point. And then I went home that night, and there's this like 2-hour-long video on YouTube by Richard Feynman, and it's just this long form interview with some guy. I think it's called Isn't It Pretty to Imagine or something, or something like this. I'll get the real name. And I was so engrossed in that. It was the most amazing thing I've ever watched. And he just went on with these beautiful explanations for really complex things. And I don't even know if it was the physics that was like, the math or the whatnot, but I think just his ability to take these really crazy things and just give wonderful explanations for what was going on.
We have similar origin story a bit then, because what really got me to physics was Feynman too. The book Surely You Are Joking, Mr. Feynman. I sat there, read it in one sitting. I was like, man, that was so cool, right? So yeah, Feynman just has a very charismatic mathematics in a way. Like the way he explained things, even though it's very complicated. Not only he showed mathematical like aesthetics, he showed us like why is it so much fun, like so much joy to do it.
I do believe it's called Fun to Imagine.
Fun
is
to
the
Imagine.
interview
Yeah, that's the one.
from 1983.
And then also I just got to shout out my grade 12 physics prof, Madamba. I think he kind of taught me you have to be a little rigorous in physics. I think I just had some good luck in grade 11, and it went well. And then, grade 12, it was like, okay, it's fun. It is fun to imagine, but sometimes you really just got to sit down and practice these problems and make sure you have the mathematical understanding. And then from there, I just haven't fallen out of love with it yet.
That's one thing I miss the most from high school, is that in high school, or even like lower year physics courses, you could just do the same problem but slightly different over and over and over, and then get really good at them. Like, think of like first year physics or high school physics. Imagine how many like free body diagrams you calculate it. Whereas like in grad school, and especially for like quantum field theory and quantum gravity, these individual problems are so complicated that even like the simplest, most baby case of like a problem in quantum field theory, it's like a 10 to 20 page calculation. So in the classes you do like one, you learn a new topic and you only do like one calculation of it. You like one example and then that's it to learn the topic. And it's like a really hard example, and you have to make so many approximations and skip so many steps because you don't have time in the class. And I just miss like doing a ton of problems, because that's how I learn. I have to do something a bunch of times in a row to learn. So like even we took it a quantum electrodynamics class, and there was one we had to do like I forget what it was, a Feynman diagram, like calculate the transition amplitude of something, and it was Compton scattering. It was like a super simple base case, but like the calculation is like just insane. And it's like, imagine like the harder ones, right? Like most people will do like their 6-year, 4-year PhD will be on like one of these calculations kind of thing. So it's ridiculous.
So this is questions for younger folks, right? Well, so when you're throughout your career or undergraduate, for example, how do you know you want to do theory and not experimental?
Right. So I was kind of blessed in the co-op program because I had really no idea. So I had quite a different balance. So I did one in Ottawa where I was really it was all kind of experimental based type thing. It was working on this facility where they'd measure Earth's magnetic field. And so it was like every day I'd have to go and set up this theodolite, and then I'd make all these measurements of where the magnetic fields were coming from, and then you'd go back and you'd tabulate them, and I'd write code for different devices. And that was kind of fun, but it was, kind of just a gut feeling, I'm not, so sure about this. I had another one in Vancouver. And here I started to realize I think I liked the theory a bit more. So my days were split there in a lab and split doing kind of just paper calculations for what we were expecting to see. And that actually I think is maybe a bit closer to where I'd like to be in the future, because it was this kind of nice break in the day. You'd do some paper calculations and you'd also get to spend like 3 hours in a lab. Labs are pretty fun environments. But of those, that day split, I could definitely tell I think I preferred just calculating pen and paper.
I'm the same way, actually. The more I get into theory, the more I kind of want to be somewhere in between theory and experiment. The best theorists, in my opinion, if you don't count like those big names who created entire theories and stuff like Einstein and whatever, but the kind of the modern day best theorists they're the people who can also do experiments, in my opinion. In my field, you get a lot of theorists who swap over to experimental stuff.
To me, it's not about being able to do experiments. It's about aware that when they do theory, they should create something that observable or have at least some theoretical predictions, or like how to measure or how to observe it, right? Well, my field is completely not that. so in a way, it's a weird thing. But because I do computational stuff, and a lot of computational stuff, what I do is just need experiments, which in a way I'm not exactly doing science in a way, but that's a story for another day. So I always ask this to our guests. So what are your hopes and dreams? Who you aspire to be? Where do you see yourself, as in your career in physics? Do you want to teach? Do you want to do PhD? Or, just in general, maybe you don't have the complete idea or picture of what your life's going to be, right? But exactly what are your hopes and dreams?
Yeah. Okay. So I think, I am signed up to do my PhD, so I'm hopefully going to complete that. After that, it becomes a little bit more vague, because there's just a lot of aspects of what we do that I really like. I have really started to like teaching. I really like research. I like just meeting with people. I like presenting. So I don't think I have a specific goal in mind. If you want to get into philosophy, I kind of try not to for a couple reasons, but there are kind of internal things that I've tried to set as goals for myself. So, there was this point in undergrad where I was becoming pretty certain I wasn't going to get accepted anywhere for a grad program. And I kind of had this realization, that all these people that I look up to in physics or outside of physics, Sagan, Neil deGrasse Tyson, Feynman. I don't think I was like interested in them just because, hey, they're a physicist with a PhD and tons of research. I think I've, admired them just because they are good at teaching and they are curious and they just kind of let them take that where it will. And so since then, and since that little stress point of, oh God, I might not get in anywhere, I've tried to just hold on to that, like just enjoy what it is that you're doing right now, because, we are really fortunate to get to do just fun research like this. But then also just realize, okay, if it doesn't go where I want it to, that's not the end of the world, right? Because these internal things, they're not something that like depend on getting accepted somewhere or a specific job. Sorry for that non-answer.
Well, it's good because I think what you mentioned is the concept of human excellence, right? You look at them, it's not because they have just like PhD or this job is that it's about how they view the world and being the best like functioning human. I think that also been kind of vague a little bit in the modern world, right? Like, oh, you gotta have this money, you have to have jobs and stuff, and the lives become less clear. I think that's a pretty good point. And PhD is a journey, and 4 or 5 years, right? You will discover a lot of things that you might talk to a lot of people who do like took the same path you took or similar path, and it would help you decide and have a more clarity. I mean, I'm still not sure. Like I'm almost halfway in. I think halfway in almost same time as Liam, right? And I'm still like, well, I thought I was set on certain paths, but things change. And maybe your PhD will be in completely different field, which is possible. Or after you finish PhD, a few like quite a number of people switch fields. My supervisor, for example, I think he worked on high energy and like string theory stuff, but now he's doing like stat mech and like condensed matter stuff. It's very interesting to hear different stories from people, and you'll figure it out.
Yeah.
So I think before we get to the story, I'd like to thank Andrew for sharing his story and his research, and I'll get Patrick to tell you everybody on how to contact us and where to find us.
Well, there are many places that you can contact us or find us. Our first of which is our email. So you can send us a podcast or an email at hyperthesispodcast@gmail.com. So if you have any questions, comments, or if you would like to be a guest, like Andrew was today, on our show, and you are researching a really cool area that you want to talk about, and it doesn't just have to be physics, it can be anywhere in science, we would be more than happy to have you on the show. We like to focus on graduate students, whether you're a master's or a PhD, or if you're a professor or postdoc or whatever. We would love to hear more about your topics. The other main place that you can reach us, if you want to message us, is through Instagram. We are at the Hyperthesis. I believe it's either at Hyperthesis or at the Hyperthesis. But you can follow us on Instagram. We post updates of when our episodes go live, as well as some behind-the-scenes looks. And Liam will occasionally post some memes, but there's no pressure for that for him. But they are really good. His Lord of the Rings one from a couple weeks ago was very excellent. If you would like to listen to us, which I imagine you're doing now, if you are hearing this, you probably know how to find us. But we are on Spotify. That's where we're based out of. But we're pretty much on any podcasting service that you can name. Apple Podcast, Google Podcast. We are on Audible. I just found out this morning when I Googled our podcast name. We are also on YouTube. We have these lovely videos that have been rendered by Feely. Thank goodness for the upgraded MacBook internals for rendering a bit quicker and a bit more efficiently. And we are almost fully caught up with our episodes. So check us out on YouTube. Give us a subscribe or a like. Leave a comment. And then we very recently are trying to have a Reddit presence, but that's in the works right now. And we're trying to expand our presence a little bit online. So there are many ways to reach us. Andrew, if people have questions for you, do you have any way that they can reach you?
Yeah, I'm a little reclusive. The best way is just by email, kovachik.andrew@gmail.com. Name spelt about how you would expect. Send me an email. I don't get a lot, so I will be sure to read it. Yeah, feel free to send any questions you have.
And if you're not quite sure how to spell Kovachik, feel free to send us an email and we'll make sure it gets to him.
All right. Thank you for that, Patrick. And thank you, Andrew. Yes, I'm slowly, I don't want to say bullying, but I'm slowly getting all of my McMaster friends to come in as guests over time. So you're I think I got, I got Josh to come in at one point. Maybe I got someone else, I can't remember, but you're one of the first, I think. So thank you for that. I really appreciate it. And I'm also, it was actually, every time I talk to you or Sergey about your work, it's kind of from my point of view, because I have a hard time understanding quantum gravity. So I try and relate it to my Bose-Einstein condensates as much as I can. But it was actually nice just hearing it from your point of view straight on. So that'll help me in the long run.
Yeah, also, thank you so much for having me. This is a lot of fun. If anyone else wants to be on, they should. They should know to come.
It's a good time talking. I always have a good time. So to finish things off, we're going a bit over time, but it's not quite a story, but I have I want to talk about two other theories of quantum gravity. We talked about Hořava gravity, which Andrew studied, but there's two big ones that most people in physics, or especially the fields of quantum gravity, know about, and that we brought up one already, which is string theory, and the other one is called loop quantum gravity. So, as we know, there's no complete theory of quantum gravity, and there's a lot of people coming up with a bunch of different versions. And the one that was really popular in the past was called string theory. This stuff is way beyond me. It's pretty mathematically heavy, so I'm not going to get into the nitty gritty of it, but I'll try and summarize very briefly what it is. And if anyone hears anything that doesn't sound right, tell me. But this is kind of like a hand waving outsider's look on it. So I think the idea of string theory is that you replace the classical concept of a point particle, so like an electron or something like that. You replace that in quantum field theory instead with these one-dimensional extended objects, or strings. So you take something that's a point, and instead you work with something that's kind of this longer, thin string. And these strings, they can oscillate with certain frequencies. Imagine a string on a guitar, right? Depending where your finger is held on it, on the what's it called, a fret, I think. Wherever your finger's on the fret, you can pluck it and it'll oscillate with some frequency which makes a noise. So these strings in quantum field theory, they can oscillate with certain allowed frequencies. And each of these different frequencies of this fundamental string actually appear as they manifest as different particles with different electric or other charges.
Interesting you say frets. Frets are more like discretization of the length, right?
Yeah,
the thing is the fingerboard, technically. Yeah.
Oh, okay. Well, like when you play a note in a guitar, there's like specific. I mean, you can go in between if there's no frets, but the idea is that each note is like a discrete frequency, and it's the same thing with these strings. I think is that they're allowed to oscillate at specific frequencies, discrete frequencies.
So it's not like the violin where you can just have continuous.
Yeah, because that's the whole idea of like quantum mechanics, is that kind of everything comes in little discrete amounts. So I think the idea in string theory is that these strings oscillate with discrete frequencies, and somehow each of these frequencies course. So if the string oscillates with a given frequency, it will actually represent some specific type of particle, and other frequencies represent other particles. So because of this, string theory promises to be a unified description of all particles and interactions based on these fundamental strings. So these strings can represent any particle. So one specific frequency will actually correspond to a graviton, which is kind of the fundamental particle that describes the gravitational interaction. So in principle, string theory combines gravity with quantum mechanics and every other theory. However, the success comes at a cost. So string theory actually requires 6 extra dimensions of space, and this is in addition to the usual 3 dimensions in space we know, plus the 1 dimension in time. So overall, string theory is a 10-dimensional theory, and I don't really know where that came from or how they came up with that. But math. pretty much. So even though it's this nice concept, it gets pretty complicated pretty fast. And the big problem, which we talked about in this episode, is that you need to be able to experimentally verify things. And it turns out the energies obtainable in our current experiments, these strings are indistinguishable from point-like particles. So there's no way you can actually tell if these strings are actual real things or what. And there's more problems than that with it, but I won't get into them because I don't really know how to describe them very well.
I will just say that for us to be able to prove string theory from a particle physics standpoint, we would need a collider that's able to produce about 10 billion times the energy as the Large Hadron Collider. So, pretty unachievable at this point.
Yes, I mean, maybe one day when we are, if we ever are able to travel the cosmos with ease, if we develop like warp drive or something, maybe we can go to some really high energy places in the universe, but who knows? So that's kind of why string theory has fallen out of favor, is that it's this kind of really nice theory that combines everything, but then you have many dimensions to deal with, which isn't too bad, I think, because dimensions are this thing that you can kind of, I mean, the math gets harder the more you have, but you can always work with higher dimensions in certain theories. Like, it's just linear algebra for people who know what that is. The next theory, however, I like this one better, is loop quantum gravity. And I think it's more closely related to Hořava gravity a little bit than string theory is, but maybe I'm wrong, I'm not sure. Loop quantum gravity has two main ideas. It uses general relativity's insight that space-time is a dynamical field and is therefore a quantum object. So it's a bit closer to classical general relativity than I think string theory is. And then its second idea, it comes back to this quantum discreteness, which determines the particle-like behavior of other field theories. So it has discrete nature, just like you would expect from quantum mechanics. Excuse me. So the idea of loop quantum gravity is that the structure of space-time is actually composed of these finite loops, which I don't quite know what that means, but I guess they're like these strings, except now instead of just going anywhere, they kind of loop back in, and so they're connected to themselves. And again, I don't quite know where that came from, but all this stuff just drops out of math at some point, and it's our job to interpret it. So we've interpreted it to be it's composed of these finite loops that are woven together in an extremely fine fabric or network. So imagine like your clothing. It's made of all these loops of thread, except now it's these loops in space-time. It turns out that the distance over which these loops evolve, it can't be any smaller than this certain minimal length scale, which actually turns out to be called the Planck scale. So this is the smallest possible distance as predicted by quantum mechanics, and I've brought this up a lot before because it's kind of related to Hořava gravity in my research. And it's a very small scale, so the Planck length is approximately 10 to the negative 35 meters, which is very, very tiny. But loop quantum gravity tells you that anything below this length scale is meaningless. So, in other words, it tells you that the structure of space-time is not actually some continuous fabric, but instead it's granular, and it's made up of kind of individual pieces. And the way I think of it, it's like water. Water appears to be this really continuous fluid of stuff. So you can swim through water, it's not like you're running through a ball pit or something. But if you zoom in close enough on the water, it's consisted of individual atoms or molecules. So if you zoom in close enough on the water, it actually looks like a ball pit. So that's kind of the same idea with this discretized space-time, that if you zoom in close enough on space-time, it's consisting of individual little pieces separated by this Planck scale. So the nice thing about this is that in quantum field theory, you often find in the math, and this is kind of related to what you were saying at the very beginning, Andrew, where you have these integrals with these 1/over frequency terms, but you get a lot of non-physical divergences, so areas where the theory fails. Imagine that you have a calculator and you type in 1 divided by 0. It doesn't really make sense, and that's a sign that your theory is failing somewhere. Turns out that this Planck scale actually it regularizes some of these infinities, because it means that you can no longer arbitrarily approach 0 infinitely close. You get cut off by this 10 to the minus 34 meters, this Planck scale. And I like that because it's a nice analogy with water, I guess, but you regulate these divergences. And that's similar to what you were talking about in your theory, but in loop quantum gravity, it's a little different. So that's a very hand-wavy summary of string theory and loop quantum gravity, which I believe are kind of the two biggest theories in quantum gravity in terms of how well people know them. Maybe they're not the most popular anymore. String theory is definitely not the most, I don't think it's the most popular anymore because of the fact you can't test it, but I think loop quantum gravity is fairly promising, although I don't know. There's some issues with both of them, like Lorentz violation, similar to Hořava gravity, which a lot of people don't like, but a lot of people do like. So it's still a very active area of research, and maybe one day we'll have a podcast episode if they ever solve it, and we can talk about that. Probably not within our lifetime, though. Who knows? All right. Well, thanks for joining us, everyone. That was a good episode. Thank you, Andrew, again, and we'll see you all next time.
Take care.
Bye, everyone.
Have a good day. Bye-bye.